Um, as if you were here last week, I talked about nucleophilic substitution reactions, but the feedback that I got was that it basically went over everybody's head, and I was trying to cover way too many topics, kind of all at the same time. And so for the next few weeks, what I'm trying to do is break down the talk that I gave last week into kind of distinct bite-sized segments that I can explain in a way that would be more accessible, and then maybe at the end put them all together. Maybe not. We'll kind of like play by ear. So today we're going to be talking about nucleophiles and see what they are. Nucleophilic reactions are probably the most important reactions in all of chemistry, especially nucleophilic substitution reactions. And so, if you want to know anything about chemistry in a deep way, the first thing to know is what a nucleophile is. Once you get out of the atomic structure and all the quantum mechanical physics stuff, you get to actual chemistry reactions and making new molecules and making bonds, breaking bonds. The first thing that you run into are nucleophiles. So what are these nucleophiles? Let's kind of take a few steps back and start with those orbitals and quantum mechanics and all that. So on slide 2, we've talked about in the past that for carbon, which is the focus of these chemistry series is organic chemistry and biochemistry. And organic chemistry is defined as the chemistry of substances that have carbon in them. Inorganic substances are the ones that don't have carbon in them. And the number of substances that have carbon in them is like several hundreds of orders of magnitude more than substances that don't have carbon in them. So for terrestrial chemistry, for chemistry that happens on Earth, carbon is extremely important. Organic chemistry is very important, and my bent for these chemistry series is ultimately getting into biochemistry and talk about that stuff. So my focus is on carbon. So on slide 2, we see that carbon has kind of 4 orbitals in its outermost shell. Orbitals we defined as being mathematical concepts that define the 50% probability space for finding an electron, meaning that at the energy level of 2px, I will find that there's 50% chance that the electron is inside of those 2 dumbbell lobes, and there's a 50% chance that the electron is outside of the
So I
dumbbell.
think, Sam, I
And
think there's no
so,
reason for you to be using insulting language here.
sorry, smart bells
Okay, there you go.
and the bells, the lobes. Is that better? Is lobe better? It's PC. So the top is for carbon atom, but when carbon goes ahead and gets involved in reactions, these orbitals rearrange themselves because from 4 different orbitals of 4 different shapes and directions, we're going to create 4 orbitals that are energetically identical to each other. And as far as orientation is concerned, they are also spatially oriented identically. So when we mathematically combine these orbitals and then come up with new ones, that's called hybridization. And because we have one 2s orbital and three 2p orbitals that are involved in this hybridization, we have an sp3 hybridized carbon. So sp3 hybridized carbon has four sp3 hybrid orbitals that are oriented as shown in the middle of slide 2. The angle between two lobes is 109.28. I'm going to introduce one more thing here, which later on becomes important. I'm just introducing it here so we can kind of, we've heard the terms and we kind of start thinking about those terms. So when you look at the sp3 hybrid orbital at the bottom, it has a big lobe to the right and a small lobe to the left. The big lobe to the right is called the bonding orbital, and the small lobe to the left is called the anti-bonding orbital. Meaning what? Meaning that if I put electrons into the big lobe, then that lobe is ready to bond with the orbitals on another atom. But if I populate the antibonding orbitals, any bond on the other side is going to get broken. So antibonding breaks the bonds, bonding makes bonds. This becomes more clear as we talk about bonding and nucleophilic attacks and backside attacks, etc., in future sessions. All right. So slide number 3.
Sam, before you move
Yes,
on,
please.
just a couple things, I guess, hopefully to kind of clear things up. I think I'm clear on this. You have in the middle there, you have both the words sp3 hybridization and the word sp hybridization. Can we just get rid of that sp hybridization, or is it serving a purpose there?
That is a cut and paste
Okay,
issue. The 3 didn't get
okay, good.
pasted. So
So,
you're
so that's
correct.
that. All right.
Let me go ahead and
Okay, so that's one thing. And then the other thing I just wanted to be clear about, because I think the picture isn't clear about it, makes it look like those two lobes that you actually have the 109-degree thing are really at 90 degrees because of those XYZ axes. So it's just really important for everybody to understand that those four lobes point off in the four directions that are the furthest apart in three-dimensional space that four such lobes can all mutually be, which is a tetrahedral kind of a shape, right?
yeah. So we're gonna see that in
Yeah.
on slide number 3.
Okay. Good.
Yeah. So yeah, that's a very good point. Those are so the thing is that the dashed lines do indicate the Cartesian coordinates, but only the vertical lobe going up and the horizontal lobe going right. Those are the only ones that kind of fall along those Cartesian coordinates, although
Seems to
Cartesian
me it's better
coordinates
just to
are,
say, to be clear, that they don't, right? You can have one
well,
of those be
yeah,
along.
but the thing is that the other two are completely off the Cartesian coordinates. These are, instead of being 90 degrees apart, they're 109.28. So if you assume Cartesians are not. All right. Yes, that is very confusing. So let's assume those dashed lines are not there and that we're actually on slide 3 on the right-hand side, where we see the tetrahedral structure That tetrahedral structure is for water. It doesn't really matter. The tetrahedral structure is the same for all of these. So we have a central atom, and then we have four sp3 hybrid orbitals at 109.28 degrees apart from each other. And so they point towards the vertices of a triangular pyramid. Uh, in this pyramid, all faces are identical, and that's a tetrahedron. Tetra for four, hedron for face. So tetrahedron is four face, and so when a carbon atom doesn't have any multiple bonds, so all the bonds around it are single bonds, the geometry around the carbon atom is tetrahedral. And we see that on the left hand side, where the two bonding sp3 orbitals have now overlapped between two CH3 moieties. And so we have formed a bond between the two carbons, and that is now CH3, which is ethane. And we also see that there's an overlap between the s orbital of hydrogen and another bonding sp3 orbital of carbon, and those also form bonds because we have orbital overlap. When we have a single orbital overlap like this, that is one orbital overlaps with one orbital, we form single bonds, and a single bond is a sigma bond. That's just the terminology there. Was that clear, John?
Yeah. Oh, yeah. Sorry, I didn't realize I was still unmuted. But yeah, I think that was pretty clear.
Okay. So we go now to are there any questions about this bonding here? Because now we're gonna make it a little bit more complicated. So I want to make sure we all understand this before we move to the next one. Okay. So slide number 4. I have now introduced the bond between carbon and oxygen, or C double bond O R prime, or in chemistry notations, R means an organic group, any organic group, but an R is bound through carbon. That's always the case. So CR bond is a carbon-carbon bond, but we don't care what happens after that bond. R prime is basically the same thing. It's another R group, and so they don't get confused. We call one R, the other R prime. And so now we have oxygen on the right-hand side, which is sp2 hybridized, and carbon also on the left-hand side is sp2 hybridized. The S, the sp two hybridized orbitals overlap in the middle in gray, and that forms the carbon-oxygen sigma bond. Well, this is sp2 hybridized. We have 3 p orbitals, so there's a third p orbital that is not involved in the hybridization. That orbital is shown in blue, and so the p orbitals now overlap as well and form a pi bond. So we have a sigma bond from the overlap of the sp2 orbitals, and we have a pi bond from the overlap of the p orbitals. On the right-hand side for oxygen, right, it's sp2 hybridized, meaning that it has 3 sp2 orbitals. One of them is involved in sigma bonding with the carbon. The other 2 carry the free electron pairs. These are additional electrons of oxygen because oxygen has 6 outer shell electrons, and so one of them is involved in sigma bonding with carbon, one of them is involved in pi bonding with carbon, so we end up with 4 additional ones. These are not involved in bonding, except they just sit there in those sp2 orbitals, and that's oxygen always has that, and that's precisely the reason water is a bent molecule, because it has those 2 free electron pairs that push the hydrogens down and make it a. So the biggest lesson from this cartoon is that what I've shown is that carbon and oxygen are sharing electrons in these orbitals, but they don't share and share alike. The electrons aren't spending time equally over carbon and oxygen. In chemistry, we have this concept called electronegativity. Electronegativity is basically it's a measure of how strongly an atom attracts electrons. The more electronegative an atom is, the better it attracts electrons. And if you look at the periodic table, which I don't have here, top right corner is the most electronegative element, fluorine, and bottom left is the least, which is cesium. So if you add fluorine gas over cesium metal, you quickly create cesium fluoride, which produces a lot of energy, and that is called an explosion. When you release a lot of energy very quickly. So cesium and fluorine gas explode when they come into contact, because cesium really wants to get rid of that electron. It has the lowest electronegativity, and fluorine really wants to get that electron because it has the highest electronegativity. So that's going to be a very rapid and energetically favorable reaction. So as between carbon and oxygen is a lot more electronegative than carbon is. And so in this, both the pi bond and sigma bond, what oxygen does is that it pulls the electrons more towards itself. And so if you were to look at this, you would kind of, I mean, if we were able to look at this, nobody has been able to do that, is that we would see the electron cloud is not an ovoid shape. It again looks like a lobe that has a narrow end over carbon and a thick end over oxygen. Because oxygen is carrying more electrons than carbon, it has it's carrying more of a negative charge because electrons are negatively charged. So if I have more of an electron cloud over oxygen, then oxygen would be partially negatively charged and carbon would be partially positively charged. This is not a full-blown charge because there actually is no electron transfer between carbon and oxygen. Instead, it's just because the electron cloud resides more on oxygen, it gives more of a negative charge characteristic to that end of the molecule. So if we look at slide 5, we'll see that we have a delta positive on carbon and a delta negative on oxygen. Delta here means partial. The small letter delta means partial. So partial positive on carbon, partial negative on oxygen. This creates a dipole moment. And if you really want to know what a dipole moment is, you ask John that question, because I just know as far as this goes, what a dipole moment is, and what it does is that it creates a polar bond. What is a polar bond? A polar bond is that one end of it has a partial positive, the other end of it has a partial negative. John, is there anything we need to know about the dipole moment?
I'm probably not so much right now, but can I back up just a little bit on slide 4? First of all,
Sure.
just one thing that you didn't go over in quite the same details with the sp3, but I think I'm right when I say the sp2 basically just, forget about one of those p orbitals. The other two are going to be in a plane, and when you hybridize those two with the s orbital, you get 3 dumbbells that are in that same plane, but now spaced by 120 degrees. Um, so that explains kind of the difference between those things. I think all that's correct, right?
So if you have three things in a line bonded to each other, the way they're as far away from each other as possible is in a straight line. The 1, 2, 3 atoms are all in a straight line. If you have four things, and that is three things are on the central one, you form a triangle that is in a plane. So every one of those point to the vertices of a triangle. If you have four, then you form a tetrahedron.
Right.
And then if you have 5, 6, 7, you go into inorganic chemistry and transition metal chemistry, and we're not going to discuss those.
Thank God. And then the other thing I just wanted, I don't know if maybe you said it, but you refer to pi bonds. Um, and I'm not quite sure. I mean, in the sense, I think just like sigma bonds, it's one electron from each of the atoms making
Yes.
kind of a 2 electron thing. But the difference is primarily because there's no real physical overlap or something. I mean,
No, there
what
is.
is
There is
okay?
this. So this is the dashed line where it says pi bond and there's a green dashed line. That's supposed to tell you that those are overlapping.
So they kind of warp somehow to,
Yeah. So what you
yeah.
end up is you end up with a lobe on top and
Ah,
a lobe on the bottom,
the important
or
thing
like an
being, right, that
ovoid.
it's not kind of in between the two atoms now, but it's kind of folding over on the top and the bottom somehow. Yeah.
I can let me see if I can. No, I'm not. I'm not gonna take the time to do
No, I
that.
think
I
that's
have
good.
cartoons of it in other presentations. I was gonna say, but for me to find which one it was and all that,
Oh,
that's gonna take a while.
and then I had one other thing. I thought at first, sorry, I thought at first you were saying that the carbon was pulling on the electrons harder,
No,
and I took
no.
that. I don't know. Maybe I just misheard. So it's the
Yeah,
oxygen. The
oxygen
oxygen's more
does.
electronegative, right?
Oxygen's more electronegative, so it
Okay.
pulls on electrons more.
Okay.
And so there's a greater electron cloud or larger electron cloud over oxygen than over carbon.
All right. Good.
So we have we're back. Anything else or okay?
No, no.
Very good. So slide 5, we see this molecule that has the dipole moment and a bond with partial positive and partial negative. Now, if I have another molecule just like this in the vicinity, what would happen? What would happen is that the delta negative of this will be electrostatically attracted to the delta positive of the other one. So instead of doing this, that, the other, let me create slide 6.
You know, and I did just notice one other thing, and it may be just a difference in terminology, but um, in physics, we would say the dipole moment of a positive and a negative charge runs from the negative to the positive.
Uh, yeah, we're not as strict as you guys are, and it's going to become clear why we do it this way in a second. So let me know. Do you guys see slide 6 as I'm creating it?
Yes.
Okay, so let me create an arrow now. Okay, so I have two molecules in the solution, and molecule 1 and molecule 2. And both of these have a dipole moment. They both have a partial negative and a partial positive on a bond. Electrostatically, the partial negative of molecule 1 will be attracted to the partial positive of molecule 2. So molecule 1, who's going after the positive of molecule 2, is a molecule that likes positive charge. Liking something in Greek is Philly, right? Like Philadelphia or phile. Positive charge is nucleo. That's where nucleus comes from. So nucleophile is something that behaves like molecule 1. It has a partial negative charge that gets attracted to the partial positive of another molecule. Now, what do we call molecule 2? This is now its positive is getting attracted to the negative of the other one. This is electrophile, meaning it loves electrons. It loves the negative charge. So we do have electrophilic reactions, and we do have nucleophilic reactions. But nucleophilic reactions, that is the way I've drawn the arrow on slide 6, going from partial negative to partial of 1 to partial positive of 2, those are much more important reactions in chemistry than electrophilic ones. I'm not saying electrophilics are not important. They are, but nucleophilic ones are more important. So on slide 7, I have basically written down what I just said verbally. So you now have a written record of what was said.
So, quick question.
Uh-huh.
It seems to me that that arrow that you draw could equally well be drawn the other way, in which case it would be an electrophilic. I mean, attraction is a two-way street, right?
Yes,
So
it
how do
is.
I don't understand quite why you call it nucleophilic.
Depends on it's a convention of who's doing the attacking. So normally uh, the species that has the electrons does the attacking because, as we said in the very first lecture, chemistry is the science of keeping track of where the electrons are. And so the electrons are on the nucleophile. The electrons move to the electrophile. So we call this because the electrons start out at the nucleophile and move towards the electrophile. We call this a nucleophilic reaction. Did that make sense?
Kind of. I think I need to just wait and see where you go. Maybe I need an example of an electrophilic
Yes,
thing.
you
Would
do,
that help?
and you won't see it for a while
Okay.
because they're both chemically and conceptually more complicated because those are done mainly on aromatic systems, and they're like things like Friedel-Crafts alkylation reactions and shit like that. And so
You know, you
uh,
drive me crazy when you use those big words. You
I
know, I can
know,
barely
I
contain
know, like
myself.
shit like that. Those technical terms. Yeah. So so let's stick with nucleophilic for now, if
Check.
it's okay.
You're the boss.
So I've shown electrophile and nucleophile here. Uh, Hold on one second. Sorry, I got a coughing fit. Um, uh, okay, so yeah, on slide 6, I've shown electrophiles and nucleophiles in terms of an acyl group, a carbon double bond oxygen. And I've shown that because it makes it really clear. There's nothing else around the oxygen to conceptually interfere with the electron withdrawing abilities of oxygen to form a partial negative charge. But oxygen carbon bond doesn't have to be a double bond. We go to slide 8 and we look at ethanol, CH3, CH2, OH. And we see that here, oxygen also exerts its electron withdrawing group on both atoms that it's attached to. One is hydrogen, the other one is carbon. And so there's a partial positive charge on both carbon and hydrogen, and a partial negative charge on oxygen. Now, if something that has a delta minus charge comes to ethanol, it now has two different places to attack. One is on the hydrogen, one is on the carbon. If it attacks on the hydrogen and it grabs the hydrogen, that's acid-base chemistry. Transfer of H plus from one molecule to another makes the H plus donor an acid and the H plus acceptor a base. So we're not really that concerned with acid-base chemistry here because that even though you could make a really good argument that that's a nucleophilic reaction, we kind of say yes, that's a very special case of a nucleophilic reaction, which is an acid-base reaction. So we're now more concerned with the attack of a nucleophile on carbon. So what happens when we do this? And we see that on slide number 1. let's say bromide, Br minus, it has 8 electrons that are just hanging out there, are not involved in any bonding. So, and it carries a full-blown negative charge. It's not partial, it's a full negative charge. So the arrows show the direction of the pair of electrons. So a pair of electrons from bromide attacks carbon, and that causes the electrons that are in the carbon-oxygen bond to leave that and move onto oxygen. So you end up with ethyl bromide and OH minus hydroxide.
Now, did you say that's a bromine ion or is it
Bromide.
bro oh, a bromide?
Bromine is the element, bromide is the ion.
Okay, right. So it is when you say a full-blown negative charge, you really mean, yeah.
Yeah, yeah, full. So,
And you
so
said
this
it
is
creates a OH ion?
OH minus. Yes, that's hydroxide,
Okay.
which is which basically makes the solution a basic or alkaline. When
And
you
if you
do this,
do basic, I would heavily suggest the Bronsted-Lewis approach in this view.
yeah, I'm not really that concerned with the definition of acid base that's being used here, because I'm more interested in the nucleophilic thing rather than the acid base chemistry that happens. So how does so this is a nucleophilic substitution reaction. Meaning what? Meaning Br minus is a nucleophile. It's carrying a negative charge. It is undergoing a nucleophilic attack on the carbon that's carrying a partial positive charge. And so that makes this a nucleophilic reaction, a nucleophile attack. And then that pushed the OH minus out. And so we substituted bromide for hydroxide. So it was a nucleophilic reaction that substituted one nucleophile for another nucleophile. So this is a nucleophilic substitution reaction.
And it's exothermic. It gives off energy because the bromine atom is much more tightly bound, I assume, right?
So that heavily depends on the reaction conditions, because in reality, the more favorable reaction is the opposite one. That is, you
Cool.
start with an alkyl halide like this ethyl bromide, and you react that with nucleophiles to make things. So this is why alkyl halides, any organic thing like ethyl, methyl, pentyl, whatever that attached to a halogen, like chlorine, bromine, iodine. Fluoride is not as good, but chlorine, bromine, iodine, those alkyl halides are starting materials for most industrial processes. Because if we look at 10, slide 10, we saw this last week. This basically shows a nucleophilic substitution reaction and names all the different components. That substrate is kind of like that ethanol that we had. Alkyl group, R, is the CH3CH2 that we had. Leaving group was the OH minus, and Z nucleophile was Br minus, and we ended up with RZ and W, that OH minus, as the leaving group. And then if we look at slide 11, we'll see basically how many different reactions, and this is just a small sampling of the type of reactions that you can do with nucleophilic substitutions. So you can see you can make anything from alcohols to phosphonium salts to tertiary amines to thioethers, right? So all of these are significant industrial chemicals, and all of these are significant biological molecules. So all of these functional groups that we're talking about, primary amines, secondary amines, phosphonium salts, thiols, alkyl halides, nitriles, all of these are present in biologically active molecules. Many of these are in the side chains of amino acids, in the active sites of enzymes. And so most of the reactions that take place inside of enzymes are these nucleophilic substitution reactions of the type that we talked about, that OH minus replaces another leaving group, or another nucleophile replaces OH minus, or what have you. So this was I'm done basically talking. This was a shortened lecture, more simplified lecture introducing nucleophiles. So John, was this more accessible?
It was right up until the very last slide there. I confess there were an awful lot of words tumbling out of your mouth there that I just don't know the definitions of.
Okay, so let's look at slide 10. Do we understand slide 10? That we have so slide 10 is really a generalized version of slide 9. Okay, in
Yeah,
slide
and
9,
I think I do understand it, but that was the start of the problem. I mean, there's the word aromatic, which you once again I don't really
forget about
know. I don't know what
aromatic.
that means. Okay, all right.
Forget about aromatic.
Otherwise, I
So
think I'm pretty good on
yeah,
slide 10. Yeah.
so basically slide 11 on top we have slide 10. We have Rx plus Z gives Rz plus X minus. Now, Rx remains the same throughout this table. Rx just means your alkyl halide. That is, R is an alkyl group, an organic group. X is a halogen, chlorobromo iodo. And Z now is your nucleophile that gets varied throughout this table. So we have Rx plus OH minus. We do a substitution reaction of X for OH. And so we end up with ROH plus X minus. That's an alcohol. What does that mean? It means that if I have an alkyl halide and I react it with hydroxide, I get an alcohol. Same thing. Alkyl halide reacted with water under basic conditions, I get alcohol. Alkyl halide reacted with alkoxide, OR minus, I get an ether, which is R on one side, R prime on the other, and oxygen in the middle. So basically throughout this, I'm replacing X with the thing that's to the right of the minus. And I see that I get that substituted product on the right-hand side. Did that make sense?
Yeah, I mean, I guess when I look at that and just kind of say, okay, it just sounds to me like it's just a bunch of examples of the same thing. I'm not sure.
Absolutely.
Yeah.
That's the point.
Okay.
That is exactly the point. That all of these reactions that give rise to all of these varied molecules that have all of these varied chemistries all of those reactions are basically examples of one reaction, which is the nucleophilic substitution reaction. And so this is there to show you why is it that we kind of harp on this nucleophilic substitution reaction, because you, as you see here, all of these functional groups, if you want to make them, you make them through a nucleophilic substitution reaction. So exactly the point was that, hey, these are just variations of the same reaction, and that's the powerful thing of nucleophilic substitution reactions. They're all the same. They're all variations of the same theme, but they give rise to the entire world of chemistry.
Yeah, so I guess the part that I get distracted by is the fact that what's an ether? What's an alkyne? What's an
Oh, yeah, yeah,
alkane?
yeah.
What's,
So
so I'm going, oh, how is that? Why is that important? But it's
no,
not
no,
really
no.
important
So
for what we're
you don't
doing
care
here.
about any of that. All
Yeah.
you care about is that, oh, I can make all these different connections with a sulfur, with a phosphorus, with a nitrogen, with a carbon, with an iodine, with an oxygen, right? I can make all of these connections using this simple reaction, nucleophilic substitution.
Sam, I'm looking at that table and I see neutral molecules being nucleophiles, and I see negative ions being nucleophiles. I'm guessing there are no positive ions that are nucleophiles as well, is there?
I'm not going to say no because I don't know, but I would say I don't recall having seen a positive ion being a nucleophile. Because to be a nucleophile, you need to have excess electrons, right? Excess electron cloud for you to be a nucleophile. And that, if you're carrying a positive charge, it's very difficult for you to have excess free electron roaming around to be available for bonding. That excess electron would probably cover the positive charge to disperse it over the molecule. So it's going to be less available for bonding, and so for that, I would say I don't think so.
All right, and one more question: do water molecules, because they are polar, do they attack each other?
All the time.
Yes.
Yes.
That's
So
sad, right?
basically, in a water molecule, you really don't know where the protons are. You can think of as water as O2 minus ions in a sea of H plus, right? Because they're all just moving around all over the place, moving from this oxygen to the other oxygen, and this is very 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 easily tested. You start with normal water, which is oxygen 16 and hydrogen, and you start with heavy water. You make it doubly heavy water, oxygen 18 and deuterium, and then you add the super heavy water into regular water, and you see the deuteriums and oxygen 18s immediately disperse
Oh,
all
that's
over the place.
nice. Oh, that's very cool.
Yeah.
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 And that happens within like femtoseconds, right?
And
It's
the way we test this is because these atoms are radioactive, so you can film it. You can actually see
yes.
the
Yeah.
wow.
Yeah, well, deuterium is not radioactive, but O16 deuterium bond has a different vibration frequency than O18 deuterium bond, which has a different vibration frequency than O16 hydrogen. It's different than O16 deuterium. So you mix this, you take an IR spectrum, and you immediately see all four vibrational frequencies in the IR.
That's super cool. Thank you, Sam.
Sure.
Another little fun fact about that water. So the pH of 7, right, logarithmically, stands for 10 to the negative 7th or something. Is that how it works out? And
Yeah.
that
Yeah.
is the concentration of both technically OH ions and hydronium H3O ions equally.
Yep. Yeah.
And
So
so the
the
moment that you have any, this is why I like Bronsted Lewis and Bronsted bases a lot more, is when it comes to this kind of, it's not really acid base, but it's kind of like neutral acidy basey, that it can influence neutral state and cause it to shift one direction or the other in acidic or basic.
Yeah, Bronsted-Lowry definition works really well when you're in water. You're dealing with aqueous solutions. Then that works well. For someone like me who works in organic solvents and not water, Bronsted-Lowry doesn't work for us. So we're mainly Lewis acid base if we're talking about acid base chemistry because we're kind of worried about what are the electrons doing, right? Who's the electron donor? Who's the electron acceptor? And so that gives us the Lewis acid base definition. But Joe, yeah, if you're doing physiological chemistry or biochemistry, those guys are all Bronsted-Lowry because you're dealing with so Bronsted-Lowry definition of an acid is something that donates a proton. A base is something that accepts a proton. And so because we're talking about proton exchange, that is more of an aqueous or in water reaction, that kind of definition works well. When you get out of that, then you're like talking about, well, I have a 2-butyl cation and I have, ammonium chloride, what's going on, then you're not Bronsted-Lowry, you're Lewis base acid base. And that definition is electron pair donors are Lewis bases, electron pair acceptors are Lewis acid. So when we look at the electrophilic substitution reaction, if you want to talk about that in terms of acid-base chemistry, we say that the nucleophile is a Lewis base and the electrophile is a Lewis acid. That that would be the acid-base explanation of nucleophilic substitution.
Thank you.
Any questions? Other topics? I mean, the floor is open. Anybody who wants to come up, ask questions?
Is there any reason why the bromide wouldn't first go towards a hydrogen as like an intermediate step, but it's just so instantaneous that it's never seen
Yeah,
statistically?
so HBr, so if Br minus grabs the proton, it makes an HBr. HBr is a strong acid, meaning that it dissociates completely, meaning that the reverse reaction doesn't happen. That is, Br minus plus H plus don't make HBr. It's always HBr makes H plus and Br minus. So in water, so so that's why it's called a strong acid. And because of that, Br minus is a horrible base in Bronsted-Lowry sense. It cannot grab a proton. That is highly energetically unfavorable, highly to the point that really dissociation of HBr in water, we say, has no transition state, has no activation energy. The HBr itself acts as the transition state. And so that makes the reverse reaction basically energetically under
Free.
normal laboratory conditions makes that reaction impossible. So no, Br minus won't do that. But if I had like ammonia in there, yes, then I would be having a competing reaction of ammonia grabbing the hydrogen or ammonia attacking the carbon. And so there I can now play with the pH of the solution. If I now make it basic, then there's no hydrogen there for ammonia to grab. And so it only now does the nucleophilic substitution reaction.
Thank you.
Sure.
It states that there is no intermediate reaction step, so that's one that would be should be first order.
Which?
This substitution should be a first order
The one we're looking at?
reaction rate.
The one we're looking at is second order. Because you don't form, because it's a secondary carbon, it's a primary carbon, terminal carbon, you're not going to form a carbocation intermediate. And so this is going to go SN2. If this was a T-butyl hydroxide, then it would go SN1. You would form the carbocation and then bromide would attach. We talked about that last week. I don't expect anybody to have any memory of that, but we did talk about the differences between SN1 and SN2 reactions. Hopefully, after we talk about all this preliminary stuff in greater detail, we can then go back and talk about the difference between SN1 and SN2 reactions, because if we can control which way it goes, then that's that's very important for a synthetic chemist. Hello, Michael. Welcome to the stage.
Hey, thank you so much for the invitation. This has been eye-opening. I haven't been involved in chemistry in a while, and I loved it when I was younger. And the way you explain things, it's very, very simple. And I watched the presentation on the Google Slides on my other phone, and it was just very easy to follow along. I still don't understand
Oh,
all
thank
of
you.
it, but I can't wait to dig in more, and I'll join you next week. My oldest son starts college this week. He's down at University of Florida. He's actually in the room. He's down in the very bottom of the room. His name is Steven. I invited him, so I wanted him to kind of get an idea of what you guys do here as well. So that was kind of interesting to share that space with him. So anyway, thanks again. Really
Very
appreciate
nice. Well, Stephen, good luck in college. Exciting time. Yeah, I envy you. I wish I could go back and redo college. I would do it so differently. I would actually pay attention this time.
it. Me too.
Sam,
Hey,
we have Sava asking to share a link. Sam, do you know anything about this? Or Sava, do you want to put it on the top or just in chat? I'm not sure.
Yeah, if you could put it in the chat, that would be great.
I have a question for Michael. I was just looking at your profile where you say you're an audio engineer. That piques my interest. What do you do?
So for most of my life, I've been involved in some sort of wiring of either studios or church buildings or auditoriums, stages. I've done a lot of different things like that. And I also delved into the medical field using different microphones, styles of microphones, to do cardiothoracic work with recording cardio sounds, whether pulmonary or getting connected to the way the heart makes sounds. It happens in so many different ranges. And if you can transmit all that information to a physician that understands it, they can make a diagnosis much quicker. So that's sort of the broad range of what I've been involved in. I'm still making stethoscopes, digital stethoscopes that are Bluetooth now for physicians, and because there's not a lot of really good ones out there. But that's sort of been a pet project of mine for a while. So I just anything to do with sound and vibrations and things like that, just really, you know,
Yeah,
interesting.
it's interesting because it sounds like it combines a lot of maybe microphone technology, a little bit of understanding acoustics with a lot of electronics.
Yes, yeah. I know you know macroeconomics and microeconomics, right? Well, sound sort of has that same realm. There are macro sound and there's micro sound. It's things that we don't get to hear that are right around us. And if you sound generator thing. We call it noise cancellation in our Bluetooth headsets now. But you take whatever the sound is that the microphone is picking up, and you take a simple guitar amplifier, reverse that signal, pump it back into that room, and you can quiet the room, no matter what the noise is that's being made. So for like a diesel engine that's really, really loud on a ship, we used to have these big, huge guitar, basically guitar amplifiers that would make the room so quiet you could hear yourself talk, even though you were standing next to a big, huge diesel engine. So that's some of the stuff that I dug into, years and years ago. But I love that stuff. I love digging into it.
Yeah,
You
cool.
may also love where they boil metals in vacuum and they deposit them using frequency into making semiconductors.
I would love to see that. I mean, obviously, vibration, any type of frequencies, materials have to react to frequencies at different, resonance and to be able to melt metal with just frequencies.
Not melt. No, they kind of like they striation the depositing of the metal into silica, and that's how semiconductors are made. Is because they create these let's call it pockets of pressure using frequency.
So, okay, I understand photolithography, etch, and chemical deprivation. So, in that type of process, where is the part that, like what you're saying, when you're attaching metal,
They have a standing wave while they're doing that. While they're boiling stuff over that, they have a standing frequency rate wave.
okay,
So does that make it like a Chladni plate kind of a situation where you're looking at the places where there's minimal disturbance or something?
And then because it's not 100% uniform in how you do it, you have specialties on how you cut the plate into different, like, chip classifications.
I've got to look into that. I used to work at National Semiconductor for a little while, so I got to dig into photolithography and etch and chemical depth and when I was not a scientist. I was in the training department, and I have dealt with a lot of interesting things. But being around about 500 doctor level scientists, I got to learn some extremely fascinating things the couple of years that I was there. So I really love listening to people talk at things that are kind of over my head because it lifts me up and gets my brain, gets the juices thinking again.
Any chemistry questions? Well, if there are no questions, we should close the room. Any news from the mods for the upcoming weeks and rooms? Any plugs?
Well, I might as well just say, I mean, so I don't know how important it really is in linking up with this, but you inspired me to look at a couple of dipole talks that I'm thinking about. One about the sun, one about the earth, and I think I'm going to talk tomorrow morning on the Bitophysics at 9:30 a.m. Pacific time, on the magnetic field of the Earth. Starting off with kind of the idea of dipole fields, both electric and magnetic, and then talking about how one generates a dipole magnetic field, and then how the Earth seems to do it, and then how that magnetic field interacts with the solar wind. So that's what we'll be talking about tomorrow.
Very nice. Okay, so have a great weekend, everyone. If I don't see you in John's room, I hope I see everyone in John's room. And I saw, did Steve Appel just come in?
We'll see him.
Maybe he came in and he left.
But
But
maybe he
anyway,
was scrolling. Yeah,
Cruising the
yeah,
hall.
cruising the hall. So,
yeah, he's back. He's back.
all right, Steve
There he
Appel, you
is.
came in exactly at the right moment. I'm playing the outro song in your honor. Unlike other times when I play the blues because of Steve Appel, I'm going to play Neil Diamond's I Am, I Said. The room will end after the song.